Our next speaker is going to be Dr. Randy Hamilton, and he's going to be talking about monitoring Aspen using remote sensing, and we've worked with Randy quite a bit here in the last year or so. He is an entomologist and remote sensing specialist working for the Forest Service's Remote Sensing Application Center in Salt Lake City, RSAC. Randy is involved with developing and testing new remote sensing and geospatial technologies for the Forest Service. So, turn it over to you, Randy.
All right. It's a pleasure for me to be here today, and I have to admit up front that I'm new to Aspen, and so this isn't my field of specialty here. So I'd encourage and welcome any feedback that any of you have as to how beneficial the techniques I'm presenting would be to you, and also how they might be modified to be more beneficial. So before I get started here, I'd like to acknowledge my co-authors, Eric Nielsen and Kevin McGowan, both at the Remote Sensing Application Center, and of course Dale Bartos. We've done most of this work in collaboration with him. So, as far as roadmap for what I'll be talking about, first of all, I want to give just a brief overview of the Remote Sensing Application Center, what it is, what we do. I'll talk briefly about remote sensing, and then I'll get into the meat of the presentation, talking about a method of monitoring sudden aspen decline across large areas, and then I'll finish out with discussing one other project where we're assessing existing aspen cover, again using remote sensing. So, Remote Sensing Application Center, we are a detached Washington office of the Forest Service, which gives us, number one, it gives us national jurisdiction as opposed to the normal Forest Service units. And we're tasked with developing and testing new remote sensing and geospatial technologies that come online, and trying to create methods to use these technologies operationally in the Forest Service. And in terms of the services that we provide, technical support, project support, training, and imagery, and many people in the Forest Service aren't even aware of what we do, and are not aware that we provide these resources for them. So any of you that are in the Forest Service, be aware that there are resources available to you. So remote sensing, in its most basic form, you can think of remote sensing as simply acquiring information about the Earth from a distance and interpreting that information. A basic form of remote sensing is aerial photography and photo interpretation. However, we typically think of remote sensing more in terms of satellite imagery and digital aerial photography and the image processing that's associated with that. So now, let me just talk briefly about why remote sensing might be beneficial for aspen management. We can answer two basic types of questions with remote sensing. One is the spatial aspect of where is aspen, or where has decline occurred. So we'd be talking in terms of a map. And then secondly, we have more of an inventory type question that we can answer, and that is how much aspen is present, how much decline has occurred. And with that, we come up with tabular type data, and we do that with statistical estimates and so forth. Some other reasons for using remote sensing. it can be an effective tool for monitoring change. You can use it as a strategic tool for identifying and prioritizing areas for restoration treatment. It can be defensible, and that's becoming ever more important. Spans multiple scales. Using remote sensing, we could look at, say, a west-wide assessment on one hand, or we could go down to a very specific area and do project-level work. We're finding that in many cases it's more economical than some of the traditional techniques for obtaining information. The digital format is very convenient because you can import it directly into a GIS. It can enhance and augment field work. And in some cases, the sensors that are on board the satellites, they can see more detail, more information than we can with our naked eyes. However, I will admit up front that it's not the silver bullet, and it's not perfect, but I will submit that it may be able to benefit many of you in the work that you're doing. So, to the meat of the presentation. This first project is involved with monitoring sudden aspen decline. So looking at change that has occurred, in this case over a 7-year period. And this was the result of a proposal that Del Barco submitted to have the Remote Sensing Application Center develop a method for assessing the sudden aspen decline across large areas. We initially selected 2 study areas. One was Cedar Mountain in southwestern Utah, and the San Juan Mountains of southwestern Colorado. As we got going with this, for the Colorado portion of this, Wayne Shepard, Jim Worrell, and Roy Mask got involved, and then Dell has a couple of graduate students working with him who got involved with the Cedar Mountain portion of this project, and that's Chad Alcroft and David Evans. And his 2 graduate students spent considerable time on Cedar Mountain this past summer collecting data. That data is not all compiled yet, so I don't have that to relate to you today, but that should be forthcoming. Most of our efforts were focused on the Cedar Mountain study area, and you can see a clone here that has experienced the sudden aspen decline. And that's a shot from 1990 going to 2000. And a lot more decline has occurred between 2000 and 2007. And as I mentioned, that's where we focused most of our work. And you can see the study area located down here in southwest Utah. Now, I'm changing my approach to this presentation around a little bit, and I'm going to show you what the results are and then tell you how we obtained those results. So this is the result from the study. This is a Landsat satellite image, and overlaid on it, this is showing up yellow and red here. There's also a lot of green in there that isn't displaying correctly. But what this layer is it's a change layer that shows the change in green vegetation between 2000 and 2007. And we used a mask to subset it down to presumably the aspen component of the forest, and this was based on the National Land Cover Data Set, NLCD. For those of you that are familiar with that, it's not a perfect mask, but given our limited budget on this project, it's the best we could do. So let me zoom in and we'll take a closer look. Here on the left, you can see this change product that we derived, and again, it was based on differencing Landsat satellite imagery between 2000 and 2007. The reds indicate areas where there has been a decrease in green vegetation, and the yellows and green indicate areas of little change to possibly an increase in green vegetation. And I've got a couple of polygons drawn here on the left that are also shown here on the right. And the right image is NAPE imagery. It's digital aerial photography, 1 meter spatial resolution. And you can see on the lower right, there's an area where the aspen have clearly died. And there's another area up in here that I've circled where presumably there's been little change in the aspen over that 7-year period. And you can see how they correspond to this change detection layer on the left. So let me talk now a little more about the methodology for creating this. As I mentioned, we used 2 dates of Landsat satellite imagery, and that was 2000 to 2007. Let me talk just for a minute about Landsat and why Landsat. There are several reasons for using Landsat satellite imagery. One, it covers a relatively large area in a single scene, as you can see here. That area is about 7.7 million acres. Secondly, and probably more important, is we have a historic archive of Landsat imagery dating back 35 years. And this is wall-to-wall coverage across the United States, collected every 16 days. So we have a very rich archive that we can go back in time and look at some of the things that have happened. Another benefit of the Landsat imagery is that it is free or virtually free and will become free and available to the public at no cost starting sometime next year. Okay, back to this slide. On the left, I've got this NAPE imagery displayed again, and this is color infrared, so the reds are indicators of green vegetation, and in this case the reds are all aspen. And on the right, I have Landsat satellite imagery displayed for 2000. And the one drawback of Landsat imagery is the resolution is fairly coarse. This is 30 meter pixel size, and you can see that much of the detail that you can see in the NAPE imagery is lost. Nevertheless, there are still patterns there that can be detected. And again, the Landsat is displayed in color infrared, so the reds are indicative of healthy green vegetation. And I've circled a number of sites. The blue circles are areas where the aspen has died. And there's one little site over here that I've circled where presumably there's been no change in the aspen in that 7-year period. Now, if you pay attention to this, the right side, I'm going to change this so it shows the 2007 image, and you can see the change that's occurring. Okay, so here's 2000. There's the same thing for 2007. Let me go back here. Watch this polygon here, 2000, 2007, virtually no change. And again, the blue ones, 2000, 2007. And you can see the decrease in the red coloration of these pixels here, showing that change. So that was the basis for this product that we derived, differencing those 2 dates of imagery. And here again, you can see a close-up of this change detection layer that we produced. Again, the reds are decrease in green vegetation, yellows and greens are no change or an increase, and how they correspond. And so far, it's looking fairly hopeful that we'll be able to detect a lot of this sudden aspen decline. But the one caution I'll throw out is that this technique is going to detect any type of change. So, for example, if you've got conifer encroachment, that's going to come into play and will actually register as a decrease in green vegetation. If you have a flush of grass and herbs and forbs under a dead clone, then that may show up as no change potentially. So there are sources of error, but hopefully it's a product that could be a benefit. So, next steps. And today, this is as far as I've been able to go with this, and like I mentioned, we had a pretty limited budget on this. We'd like to take it farther, but our budget is limited. But the next step to this would be to validate it with field data. And fortunately, thanks to Dale's graduate students who have been willing to share their data with us, we'll be able to do some validation. One way I would recommend taking this to the next step is to stratify that change detection layer that I showed and divide it up into maybe 10 equal interval strata. And then within each one of those strata, go out and randomly sample with either field data or potentially photo-interpreted data. And based on that sample, you can derive an estimate with confidence interval of the amount of decline that has occurred in each one of those strata. And with that, you have not only the map, but you also have a very solid estimate of how much aspen decline has occurred. And here's an example of how you might stratify an area based on that change detection product. Now, given that I didn't have the data yet to validate, I went and did just a quick and dirty assessment of this. And I selected about 20 random points in this change detection layer. And then just visually made a guesstimate of the percent loss in canopy cover, going at 25, 50, 75, and 100%. And then on the y-axis, this is the values in the change detection layer. And you can see there's definitely a relationship there. It's not as strong as I'd like to see. Hopefully that will be strengthened with the field data, but there's definitely a relationship there. Okay, with that, I want to just summarize briefly and then talk real quickly about another project. In terms of the product that is derived from this, you get a spatial layer showing change in green vegetation, plus you can augment that with a statistical sample and an estimate of the decline that has occurred. In terms of cost, the imagery is, for all purposes, free of charge. The image processing is very straightforward. It wouldn't take more than a day or two to do it unless you wanted to refine your aspen mask and do a classification based on the historic data, and then you could run into a considerably more time. Then the other portion of the cost is your field and photo sampling, and that can be quite variable depending on how you do that. Benefits, you get a large area coverage, it's relatively inexpensive, and it's defensible. Okay, let me shift gears just briefly. This is a similar project in the Custer National Forest, where we were asked to document the existing aspen, not looking at the change, but just document where and how much aspen is currently in the landscape. And that's part of the greater Yellowstone area. And we started out with a pilot project. Since then, the forests were able to come up with some additional funding and have asked us to extend this to the entire Gallatin Forest and the Beartooth Ranger District of the Custer National Forest. It's about 2.7 million acres we're going to be doing this over. So they felt like they didn't have the information they needed on the location and extent of the aspen in order to make management decisions, and that was the rationale for this project. We again used Landsat imagery, did a stratified classification of the Landsat imagery, and the strata represented different proportions of aspen cover, starting out at about a 0 to 17% cover on up to near 100% aspen cover. And you can see the comparison with the classification on the left to NAPE color infrared imagery on the right. And I'm not going to go into the details of how we did that classification, but just consider it was a stratified map of aspen cover. We then went into each of those strata and did a photo interpreted sample of each of the strata using digital dot grids. So we're kind of going back in time and resurrecting the dot grid sampling techniques, but in a digital world. And based on these dot grid samples, and you basically just indicate wherever you have a dot hitting an aspen tree, you count that, and you can get an estimate of the amount of aspen within each of those strata. So here's the pilot study area, and again you get a spatial layer indicating the location of the aspen, plus you get tabular data which gives you an indication of the amount of aspen with confidence interval within each one of those strata. So the product, again, you get a spatial inventory layer. It shows where the aspen is, plus you get the tabular data indicating how much aspen you have. In terms of cost, this is also relatively inexpensive compared to doing this all in the field or by photo interpretation. Imagery's free. Image processing is actually a bit more intensive on this, so you may spend 3 or 4 weeks with that, and then you've got your field or photo sampling, which is fairly variable on how much time that will take. You get a large area coverage. It's again relatively inexpensive, and again a big plus, it's defensible. So in conclusion, remote sensing provides tools for monitoring change in aspen. It's defensible, spans multiple scales, and you can use it to help identify and plan aspen restoration projects. And in many cases, it may be the most economical option to obtain information across very large areas. So with that, if I have time, I'll take any questions. Yes?
For both projects, what was your minimum mapping size?
Minimum mapping unit was a single Landsat pixel, which is 30 by 30 meters. Yes?
Sense of the difference in signal between an aspen canopy and
they're pretty difficult to distinguish with the 30-meter pixel. Again, with our limited budget, we didn't have the opportunity to explore that as much as we would have liked. There may be some differences, but based on our experience with vegetation mapping in general, it gets to be fairly difficult to distinguish those. Probably the best chance of that is getting imagery late in the fall, where potentially the herbaceous vegetation has died down a bit, and allowing you to distinguish it a little better from the aspen. Yes?
How does the change in leaf color affect the imagery if you did it late in the fall?
Well, if you do it, well, there are two things going on. If you do it at the right time in the fall, potentially the changing colors of the leaves can help you, but the downside to that is when you've got an elevational gradient, you've got those leaves changing colors at all different times. So that can be a benefit and a hindrance. So in terms of mapping and distinguishing the herbaceous community from the aspen, you've just got to hit it probably right before you start getting the leaf color changes. Go ahead in the red.
I had a question for you. For your change detection, did you use NDVI or some other index?
It's actually a combination of NDVI and NDMI, which is Normalized Difference Moisture Index. Yep.
So, if you have these archived images, are you able to look at climate associations? So if you just route maybe an important look each year and maybe make those connections, have you been able to do that with the RSAC?
That's not something we've been able to look at, but I believe is Dave looking at? Yeah. Yeah, Dale's got one of his graduate students will be looking at some of the climate implications and the year-to-year change. Yes.
I'm more interested in conifer encroachment. Have you considered using Landsats for winter time to look at in what was historically aspen habitats from like the 2001 NLCD, and looking at conifer or green on those in the winter photos at all?
That's not something we've done. That is a possibility. The one difficulty with that is the snow, and that can be a fairly confounding factor, although there's still the possibility of detecting the conifer against the snow background.
Okay.
Thank you.